In this video we will see stress and strain. So first of all, here we see to calculate stress and strain we have to do an experiment in universal tensile machine. Here we have this specimen and it has a bigger diameter. This can be also a square or a circular or a rectangular body, but for now if we consider this as an circular, then here is the bigger diameter. Here there will be smaller diameter in between, and there is a smooth transition so that there is no stress concentration. So on this bigger diameter we apply the load, and because here there is a bigger diameter, the stress will be higher in this section where there is a gauge length. So between these two marks, there are two marks on the specimen, is called as gauge length, where we are taking our measurement, and this is called as a parallel length, from which the cross section starts to change, and overall length is from end to end of this specimen. So now here the load is applied at the end on the bigger diameter. So this is called as a grip end, where we hold it in the machine and we pull it, we give a tensile load, and the load transfers to this smaller cross section because more stress will be here, because load P is throughout same on the each and every cross section, but smaller the cross section, there will be more stress because the stress will be P upon A. So here is the smaller cross section, so more stress will be here. Now you see here A naught is the initial cross section, so here the area, cross sectional area, will be A naught, and instantaneous area means after we pull it, there will be phenomena in which there will be reduction in cross section. So at that time we will say that AI will be the instantaneous area, means at that particular time what will be the area which we call as AI. So A naught is an initial area before starting the experiment. Now once we pull it and we plot the P versus delta L diagram, so to calculate the delta L, there is instrument called as extensometer. Extensometer is used to measure the length of the specimen at particular instant, and it gives the change in length also. So here we calculate the change in length with respect to load, and we plot the graph, and then we plot one more graph where we divide P by A naught and change in length divided by original length. So we get a stress versus strain diagram. So first we plot P versus delta L graph, and then we plot stress versus strain graph. So now we plot this stress versus strain graph. Here E means engineering, so it is engineering strain, and this is engineering stress. So here if you see, first the stress starts to increase up to A point, which is called as proportional limit. Here stress is proportional to strain. Then at B point it is elastic limit, means up to that point, after unloading up to this point, the material will not have any permanent deformation, it will again come to zero strain. At C point it's called as an upper yield point, where the yield strength is there, which is upper yield strength. D and E point are lower yield strength, and F point is an ultimate tensile strength, and G point is where finally fracture occurs. Here triangular area up to A point is called as proof resilience, and any triangle in between these 2 points, if we take point here and we form a triangle, then it is called as resilience. But at A point we call as proof resilience, and in stress strain diagram we call as modulus of resilience, because resilience and proof resilience are for P versus delta diagram, but in stress strain diagram we call as modulus of resilience. And the total area from this particular graph, the inside area up to point G, we called it as in toughness of this. Now if we see here, we got a C point where there is upper yield point, and D point where there is a lower yield point. So this phenomena is due to Cottrell effect, and we call it as in Cottrell atmosphere, because if you see here the atoms arrangement, this blue color are the atoms, and there are carbon and nitrogen impurities in steel. So in carbon and nitrogen impurities are at interstitial sites between those atoms. Now if you draw these lines, we see there is a line or edge dislocation which go inside the plane. So this is inside the full plane of atoms which are having dislocation here. So these are the entire planes, but this is a half plane, and here there is a void, means there is a bigger space available. So when we give the load to our specimen, then what happens, this carbon and nitrogen atoms at this particular location have compression. So if we stretch it in any direction, this particular atoms will have compressive loads, and it tries to find the space. So so there will be much more load increased up to the point C, and after that one particular point, what happens is, this location has to move. So here there is a bigger space available, so this edge will not transfer to with these atoms, and it will not glide out on the edge boundaries, because there is a much bigger space, so more energy is required. Now what happens, once this compression is greater than certain limit, then this carbon and nitrogen atoms will come to this location, because they can get a much bigger space here to accommodate. So they will try to come in this location, and after that this carbon and nitrogen which are hindering this particular edge dislocation to glide, and also there will be much less energy required to bond with other lines. So this particular edge dislocation will glide through other planes, and this atom will connect here, then this atom will connect here. So likewise there will be three atoms at the grain boundary. So like this, after this cortical atmosphere is break, and all the carbon and nitrogen atom comes in this space nearby atoms, then there is a reduction in the stress, which we can say that stress reduced from C point, upper L point, to lower L point, which is D point. And what happens is, if there are more number of these edge dislocations, then more number of cortical atmosphere is formed, and after certain points, due to accumulation, there is a sudden reduction in the stress. But this is only for carbon percentage less than 0.3. More than this carbon percentage, there is immediate cortical atmosphere break, and due to hindrance of the there is actually more number of carbon atoms, there is more hindrance in the dislocation motion itself. So that's why this phenomena is only happens in mild steel or carbon percentage having less than 0.3. The interesting phenomena other is D to E point. There is a constant stress from D to E point for some time, for some strain. So for a certain limit of strain, there is a constant increasing in strain for certain value of stress. So here D to E we call as Luder effect, because there are Luder bands formed at 45 degree inside this material, and until this full material is filled with 45 degree Luder bands, this stress will remain constant for certain strain. So 45 degree Luder bands are formed in this material, and it called as Luder bands. Now if we see here, up to proportionality limit, which is A point, stress is proportional to strain. So here stress is equal to E times strain. So sigma is equal to E epsilon. So here E is a Young modulus, which is the slope of this line. Now if you see here, engineering stress and true stress. So here engineering stress sigma E is equal to simply P divided by initial area A naught. So whatever the initial area is, at every point we have to divide it by A naught. And engineering strain is delta L by L naught. L naught is the initial length of the specimen. So these are engineering, which we have plotted here. Now if we calculate true stress, so which is sigma T, we have to divide load by instantaneous area, not by the actual or initial area. So here instantaneous actual area will be there. This is called as an initial area. This is actual or instantaneous area of the specimen. Instantaneous means with the strain, it is reduction in area will start. So that we have to divide here. So if you multiply both A naught by numerator denominator, then we can calculate this formula, that P by A naught is sigma E engineering stress 1 plus engineering strain. So that is a true strain. So you have to remember this particular formula, that true strain is engineering strain 1 plus epsilon engineering. Here small, if we take a small dl length, and if we calculate true strain, then it will be simply dl by L instantaneous. Now if we integrate it, epsilon T true strain, then we get dl by L is ln 1 plus epsilon E. So these two are almost similar, 1 plus epsilon E, 1 plus epsilon E. Here we have sigma E, here we have ln. So this is how you can remember this true stress. and there is a different graph for true stress and true strain, and we'll see in future videos. Thank you for watching this video, and see you in the next video.